This is the second video on the comparison between Fourier and Laplace transform. In first video, we have seen the mathematical relation between Laplace and Fourier transform. So here we will see some comparison between Fourier and Laplace transform. So Fourier transform is a special case of Laplace transform, or we can say Laplace transform is generalized Fourier transform. So how we can say this is uh, x, which is the Laplace, this is the mathematical expression for the Laplace transform. Here xt e raised to minus st dt, integration minus infinity to infinity. In place of s we can put sigma plus j omega. Then if we split the exponential, you will get this part. And you can observe here that if you put sigma is equal to 0, you will get this expression, which is nothing but the Fourier transform. So Laplace transform is a Fourier transform when sigma is equal to 0. Means sigma is equal to 0. So it is the special case. So Fourier transform is a special case of Laplace transform, because in Laplace transform transform sigma value, you are putting sigma is equal to 0, some specific value you are placing there. That's why we can say that Fourier transform is a special case of Laplace transform, or Laplace transform is a generalized Fourier transform. Then second is Fourier transform cannot be applied for analysis of non-absolutely integrable signals. But we can apply Laplace transform for the analysis of non-absolutely integrable signals. For that, you should know what is absolutely integrable signal. So absolutely integrable signals are those whose area is finite, whose area is finite. How you are going to find the area? By integrating minus infinity to infinity mod of that signal dt. If that is less than infinity, then that signal is absolutely integrable. So here we are saying that Laplace transform can be applied, cannot be sorry, Fourier transform cannot be applied for non-absolutely integrable signal, and we can apply, or we can use Laplace transform for the analysis of non-absolutely integrable signal. So absolutely integrable means its area is finite, the signal's area is finite. And non-absolutely integrable means its area is not finite, that signal is growing. So absolutely integrable means finite area. Now for this we should take one example, then only we can understand this concept. So for that we have taken here one example. Xt is equal to e raised to 80 ut. So this is first we will check whether this is absolutely integrable or not. So you will understand how to check absolutely integrable signals or not. So xt is equal to e raised to 80 ut. So for that you have to compute this thing. So this, what is this? This is area of that signal. So mod xt dt, integration over minus infinity to infinity. So here xt they have given as e raised to 80. We have placed the value e raised to 80 ut dt. Ut after that we utilized this concept that mod ab is equal to mod a into mod b. So we have splitted this mod into two mod operations, e raised to 80 mod ut. After that, we have removed this ut by changing the limit from of minus infinity to infinity to 0 to infinity, because you know that ut exists for the positive values. After that, and after this, we have removed this mod also, because all exponentials are positive. How? If you see, this is your e raised to minus 80 signal, and this is e raised to 80. So all those are above the horizontal line, or they are positive. That's why mod is removed. After that, if you solve this integration, you will get this one, 1 by e raised to 80, 0 to infinity. That is e raised to ax is 1 by a e raised to ax. Then if you place the integral limits, you will get the get e raised to infinity minus e raised to 0. E raised to infinity is infinity, e raised to 0 is 1, so answer is infinite. That means this signal's area is not finite. So this is not absolutely integrable signal. So we have seen till now we have seen that how to see whether the signal has finite area or whether the signal is absolutely integrable or not. For that you have to compute what? You have to compute this integration. Okay, so we have one signal and we have found its absolute integration. We have found its area whether it is finite or infinite. So we have seen that its area is infinite, so it's not absolutely integrable signal. So we are saying that Fourier transform of such signals is doesn't exist, or we cannot analyze such signals with the Fourier transform. For that we have computed the Fourier transform. Fourier transform equation is x omega is equal to minus infinity to infinity xt e raised to minus j omega t dt. So all these equations are already discussed in lecture 1. So you can check that lecture also. So x omega is equal to, this is your xt e raised to minus j omega t dt. Again ut we have here simple integration is there. Ut is replaced with integration 0 to infinity because ut exists for the positive side only. Then e raised to at e raised to minus j omega t. Then we have combined these two and we got this one. After that we solve the integration. You know that this is 1 by a minus j omega e raised to t a minus j omega 0 to infinity. So if you put the values, you will get again e raised to infinity, that is infinity. So x omega is equal to infinity. So Fourier transform of xt does not exist. There are exceptions, but we are not going to discuss those exceptions here in this lecture. So we just want to say that most of the time if signal is not absolutely integrable, that means if signal's area is not finite, Fourier transform is doesn't exist, or we cannot analyze the signal with the Fourier transform. Then let us see what about the Laplace transform. We have already seen that Laplace transform is nothing but the Fourier transform of that signal multiplied by e raised to minus sigma t. So in Laplace, while before finding Laplace transform, we are multiplying that signal with e raised to minus sigma t. Uh, and then finding the Fourier transform. So for that, and we know that Fourier transform of absolutely integrable signal exists. So first what we will do, we will check whether xt e raised to minus sigma t is absolutely integrable or not. The purpose of solving that is we have to comment whether the multiplication with e raised to minus sigma t makes the signal converging, or whether whether we can get a region where we can say that the signal is absolutely integrable or not. So only thing you have to remember here is that Laplace transform converts the signal xt into xt e raised to minus sigma t, and after that it takes the Fourier transform. So xt is modified to xt e raised to minus sigma t. So we will let us check whether it is absolutely integrable or not. So if you I am going to provide you the notes of this whole PDF in the description box. You can refer those. Here I'm not going in much detail of the integration because it's very easy integration, and already I have explained all these integration steps. So for finding the absolute integration, we have to do this. That means minus infinity to infinity the signal mod dt. Okay, so e raised to a t ut is your signal, then multiplied with e raised to minus sigma t dt. Then this is used and splitted the mod signal. After that we have combined this and this, you got this one. After this you get this, ut is replaced with 0. Then solved the integration. Integration e raised to ax is 1 by a e raised to ax. Same way, this is the integration. We have placed the integration limits, but here we have the chance, we have we know that A is positive. We have the chance that A minus sigma can be negative, because sigma value varies from minus infinity to infinity. So A minus sigma can be negative also. If A minus sigma is negative, then we will get this e raised to infinity a minus sigma equal to e raised to minus infinity a minus sigma, that is equal to 0. And for positive values of a minus sigma, you will get e raised to infinity as e raised to infinity. There in the Fourier transform there was no chance, because there is only a term is there, and a is already defined at it is positive. That's why here there is a chance that you will get this term as negative. If you get this term as negative, then you know that e raised to minus infinity is equal to 0. So there is a chances that you will get some answer, or you will get some value. And you have solved it. E raised to minus infinity is equal to 0 minus 1. You got this answer 1 by sigma minus a. So, but under the condition a minus sigma is less than 0, that is called region of convergence. This is called region of convergence. So that is the concept in Laplace transform, that Laplace transform multiplies the signal with e raised to minus sigma t and make it to converge, or make it absolutely integrable for some region, and that region is indicated by sigma value or real value of s, that is ROC concept. So we have seen here mathematically or with example that Laplace transform converts Laplace transform converts the signal into absolutely integrable signal by multiplying it with e raised to minus sigma t. It makes it to converge, or it makes it to give some value. So after that we will find the Laplace transform, and we know that after that we will find the Fourier transform. And you know that if the signal is absolutely integrable, then definitely Fourier transform exists. That's why Laplace transform exists. So here the expression of Laplace transform is there: e raised to at ut e raised to minus st. This is 0 to infinity e raised to at e raised to minus st. After that, just simple mathematics is there. We have solved this. Then you will get here the all the integrations are as already discussed in this video only. So t a minus s dt, you get this one. And here you have to we have just I have just used here the value of s as sigma minus j omega to show you that because of sigma you will get a region of convergence, because after that this a minus sigma minus j omega. So here a minus sigma, if it is negative you will get here minus infinity, and you will get the answer. So a minus sigma, the same is written here. So you will get e raised to minus infinity, that is equal to 0. So you got the answer as xs is equal to 1 by s minus a, and region of convergence is a minus sigma is less than 0, or real part of s, that is sigma, is greater than a. So when you solve the examples on Laplace transform, there is no need to write here sigma minus j omega. I just want to show you that this is nothing but a Laplace Fourier transform of e raised to minus sigma t, because if you solve it e raised to 80, then e raised to, you will get here, one second, you will get here e raised to 80 into e raised to minus sigma t into e raised to minus j omega t. So Laplace transform is nothing but the signal multiplied by e raised to minus sigma t. Sigma t is Fourier transform. That's why I have written here that s is equal to sigma minus j omega. When you solve the problems of Laplace transform, there is no need to write here sigma minus j omega. We have to show that region of convergence depends on sigma. That's why we have written here s value, and here we have not written it because that is not necessary. So what we have seen that for non-absolutely integrable signal, Fourier transform does not exist. There are exceptions. We are not going to discuss those exceptions here, but most of the cases for non-absolutely integrable signal, Fourier transform does not exist. For that, we have taken one example, e raised to 80 ut. And we have shown that that is not absolutely integrable signal, that doesn't have finite area, and we have also shown that its Fourier transform does not exist. Then in Laplace transform, we are multiplying that xt with e raised to minus sigma t. Then after that, we have seen whether that signal xt e raised to minus sigma t is absolutely integrable or not, and we have shown that it is absolutely integrable. That means it has finite area over some region, that is called region of convergence, that depends on the real value of s, that is sigma. So after that, we have seen that if it is absolutely integrable, then Fourier transform exists. That's why Laplace transform, and Laplace transform is nothing but Fourier transform of xt e raised to minus sigma t. So Laplace transform exists, and we have shown also what is the Laplace transform value and what is its region of convergence. Then next point is Laplace transform can be applied to broader range of signals. Yes, because it includes non-absolutely integrable signals also. Fourier transform is evaluated on j omega axis, while Laplace transform is evaluated on entire S plane. So this is your S plane, where on x-axis there is sigma, on y-axis there is j omega. And in Fourier transform, sigma is equal to 0. So sigma is equal to 0 means this axis only, j omega axis. So Fourier transform is evaluated here and Laplace is evaluated over entire S plane, because for Laplace sigma is anything, it is general. Okay. Then specifically for system analysis, again one thing is that Fourier transform is used for signal analysis mostly, and Laplace is used for system analysis mostly. Why? Because in the Laplace, S is equal to sigma plus j omega. So in Laplace, variable is a complex variable. So doing signal analysis with the complex variable is complex. That's why we are preferring j omega only. That is, we are preferring Fourier transform only for the for the signal analysis, because we can do the signal analysis with the Laplace transform, but it becomes complex. So why to go for the complex if we can do it with the Fourier transform? So mostly Fourier transform is used for signal analysis, and for system analysis we use the Laplace transform, because there is no any variable indicating the system's response or system's pose, zero, stability, and all those things in the Fourier transform. That is there in the Laplace transform, that is the sigma value. So Laplace transform is mostly used for the system analysis. We cannot use Fourier transform for system analysis, but we can use Laplace transform for system as well as signal analysis. Now, limitations of Fourier transform, this is very simple. It cannot be used for non-absolutely integrable signal, then broader range of signals, then differential equation solving is difficult. Again, you know that for the system analysis, this is your LTI system's impulse response. This is your XT. This is your YT. Output is YT. So Yt is equal to Xt convolved with Ht. So in Fourier transform, we convolution is nothing but the multiplication in Fourier transform, x omega into h omega. So convolution is equal to x omega into h omega. But this is somewhat difficult to do, although it is a multiplication, but it is difficult than the Laplace transform. So need of Laplace transform, because we have to do the analysis of non-absolutely integrable signal, that's why Laplace transform is needed. Again, broader range of signals. Then differential equations solving is very easy with the Laplace transform, and also performing convolution. Just now I have told you that system response ht, its input is xt and its output is yt. So YT output is nothing but convolution of impulse response into its input. So in Fourier, in frequency domain, it becomes H omega into X omega. It becomes this is convolution. It becomes multiplication in Fourier domain, or sorry, frequency domain. But it's very hard with the Fourier transform. But this multiplication is easy with the Laplace transform. So this is the different or comparison between Fourier and Laplace transform. We have taken example, and with that example we have tried to explain you the meaning of each comparison. So I hope you find it useful, and if in further videos we are going to cover much and more topics in signals and systems and many electronic based topics. So if you like this video, then subscribe to the channel, so you will get much more interesting topics or much more useful topics in the electronics based subjects. Thank you.